So hello everyone, my name is Bernardo Cordovez. I am Gregorio's alter ego here, quite not as sexy and can't play the guitar, but hopefully I'll entertain you today. That's right. So following what Julian said, I'm pretty honored to be called an expert in nanotech. I'm actually a nanotech entrepreneur. Can you guys hear me well? Now you can hear me well. I'm a nanotech entrepreneur. Started a company called Optofluidics. And we basically make science fiction science fact. And our goal is to commercialize technologies for quality control in many, many different and emerging fields in pharma, as well as nanotechnological particles that researchers are making every day. So my objective here is to tell you how cool nanotechnology is, why all of this buzz around nanotech, what does it mean anyway? And hopefully you'll take some of that and say, okay, well, maybe we should pay some attention to it. So what is nanotechnology? To tell you the truth, there is no definition. Nanotech is something that actually lives in the academic environment for the most part. So given that it's pretty much, for the most part, an entirely academic endeavor, professors love to come up with definitions of what nanotech is. But because it's so dense, there's really no way to encompass it. I think my favorite definition is that it's the manipulation of matter between 1 and 100 nanometers. So what does that even mean? So a nanometer is actually 1/1000th of a meter, and in the US of A, that's 3 feet. So basically, to give that some context, we're talking about very, very small things and exploiting the functionality of those very small things to make meaningful engineering results. And if you look at this chart up here, researchers in nanotechnology work with nanoparticles. To give you an idea of something on the nanoscale, like a protein is on the order of, say, 5 to 15 nanometers. So if you were to look at the ratio of the size of, like a 1.8 to 2 meter tall human being to something like a nanoparticle, like a protein, or in the field, something people call a quantum dot, it's equivalent to how many tennis balls you could basically align throughout the diameter of planet Earth. So these are very, very small things, and just to give you an idea of the scale. So okay, so things are small, but so what does that mean? So actually they're very, very small, but it's at this very interesting junction between the atomic scale and the macro world that you and I live in. So when we look at materials, we kind of understand how they work, right? They bend, they break, etc. But when you think of atoms, it's a little bit different, right? And this is actually at the point in which those two worlds kind of collide. So it's at the scale in which materials start getting their bulk properties. So you can do a lot of very, very interesting types of engineering and ways to manipulate them to yield meaningful results, hopefully for the betterment of humanity. So because the subject is so dense, I picked a couple of case studies of why I think nanotech is interesting, and some of the most popular nanotech subjects. The first one is nanotubes. It's on the top left corner. I don't know if you guys have heard of what a carbon nanotube is, but researchers have been able to synthetically make new materials, literally one atom at a time. And these carbon structures, which researchers engineered, can be stronger than diamonds, so they're the strongest things ever. And in addition, they can conduct electricity more than any other structure known to man. And the reason for that is that, again, it's because of this interface, right? You're at the point that the atoms actually start behaving almost like as a bulk structure, so you can get things called ballistic movement. Things just, atoms, electrons just whiz by. Comparing it to your traditional, electronics. So it's pretty groundbreaking. Another case study that I quite like is the invisible cloak. Maybe you guys have seen The Invisible Man. It's probably taken many different types of adaptations to this point. But you can actually engineer materials that behave in a way that they would never, ever behave in nature. So there's two ways of looking at nanotech, right? So making materials to behave like biology. In some way, those are called biomagnetic, or other ones. You can actually engineer materials that you would never, ever see in nature, and you can actually do them. One of such materials are called metamaterials, and these materials can basically guide light in such ways that, for example, if I were to shoot a spotlight right here at my wife, right now I can see my wife because the photons in this room are impinging on her and then bouncing back, right? So what I actually see is her reflection. I don't really get to see her, but if she was coated with such materials, basically the light would go around her almost like circumventing her. So I would never actually be able to see her because what we see is scattered light. So if you have a way to actually guide that light, you could actually make something like an invisible cloak. And the only way to do that is to engineer materials that do that, and that's only possible in the nanoscale. So again, this is unique physics that just doesn't happen in the atomic scale, and unique physics that doesn't happen in the macro scale. But to go with the buzz, there's a second component, which is essentially a functionality component and an economic component. So by functionality, I mean you can make sensors that have, for example, on a biological level, you can have assays that can test for all sorts of different types of diseases in a single chip, in a piece that is about 1 inch by 1 inch. And in addition, because nanotechnology, for the most part, borrows what the semiconductor industry, your chips that you use in your iPhones and computers, which is this top-down approach that basically used all of the advances in photography to be able to make very, very small devices. So as a result of that, you can make a lot of these, and if your idea is really, really good, there's no better way to mass produce things, right? So you can get a lot of functionality, and the economics actually make sense. So not only is there unique physics, and there's actually money to be made. So why don't we tie these two together? So that's one of the main reasons why nanotech has been really looked well upon by society. So my role is, I'm a tractor beams entrepreneur. Do I have any Trekkies in the audience? God bless you all. In Star Trek, I think version 1979, not the 2014 or whatever it is, there's this concept called a tractor beam that the Starship Enterprise can launch a beam of light and trap a Klingon ship at a distance, right? That's been seen in a lot of sitcoms like The Simpsons, where Homer is actually being hovered by a ship, or even at Star Wars. But that's, as you know, that's all science fiction. But what they found, researchers at Bell Labs about 30, 40 years ago, what they found is that you could actually do that, but not in the macro scale that you and I live in, but if you were to shrink things down, you could actually use light, the photons, right? So like the particulates that make up light, to actually move about materials. And that was pretty cool. So, but it's kind of a confusing thing, right? So you guys may have heard of something called a solar sail. So you put like these huge sails out in outer space, and then basically just a sunbeam just hits it and basically sails along. So it's easy to understand why these little photons, if in fact they're little particles, why they can push on something. But actually you can get these optical beams to trap stuff, not only to just push, but to trap. And we exploit that phenomena actually to analyze very, very small particles for this up-and-coming field of nanotechnology and in very, very relevant fields of biopharmaceutical processing. So if I were to show you what I do for a living, imagine you're these tiny little nanoparticles. These are viruses and proteins, and they were being funneled through this tiny little tube into what our technology is, which is a tiny little flow cell with small-scale optical fibers patterned on a substrate, on a piece of silicon, just like you pattern a computer chip. And these little flat lines there, they basically guide light. So instead of guiding electricity like a computer chip, our chips actually guide light, laser light. And they are almost like this protein vacuum cleaner that they suck the particles into a specific location. And once they're there, they basically interact with our technology. They scatter a lot of light. And if we turn the laser light off, we can basically manipulate things. So we're a magnet that doesn't necessarily work on magnetics. We can trap any very small particle, bring it to where we want it to analyze it, and then once it's in our technology, basically it interacts in such a way that you can get that you can characterize these particles. By characterizing, I mean understanding what they are, both physically and chemically, and that's really important for quality assurance procedures in which you really need to understand what you're looking at. So. Just to confuse a little bit more, so we make little tractor beams on a chip. Our technology is actually, the core of the technology is literally a chip, just like a computer chip. It's a little flow cell, and it has these little optical fibers at the bottom. So if you were to look at this, I don't know if you guys have ever looked at a microscope. Maybe you haven't. It's actually something pretty cool. But what you would see is that these particles are actually not only captured, but they start gliding on on these little trapping sites. So we look at how they interact with our technology, and we extract a lot of information from those particles to tell the researchers what they're looking at. So in essence, we make tools for researchers across academia and in the pharmaceutical field as well. and then we process that data to understand what these particles are. So we're actually taking concepts from science fiction and applying them in science fact to extract meaningful information from these tiny little particles. Again, this is what we make. We just launched in January, actually, and at the beginning, we were essentially funded through government grants. There's these grants, the competitive grants, that are set out for small businesses to, for the most part, translate technologies from academia and into the marketplace. And in addition to that, we were also venture-backed, but now we're venture-backed, which means we've got to start selling something. And we've done actually a pretty good job at that at this point. So what are some of the barriers for nanotech? I can be a little bit opinionated, but I think there's two big barriers. So I guess on a higher level, people don't, including myself, we don't really understand all of the capabilities of nanotech. So all of these tiny little particles that are fabricated by people, they could actually be, in some ways, they could not be healthy for you, right? They will just pierce through your skin and possibly go to places that you don't want them to go. So what we're actually building is the compliance tools that get people to understand what's actually happening. What are these particles that you're studying? So on a fundamental level, there are no regulations for nanotech for the most part. So those are barriers that will come and the field is going to face. From something that a little bit more close to, I think that probably the biggest barrier to nanotech is twofold. The first one is that even though Julian rightly pointed out that it is one of the highest funded fields in science, science as a whole is completely underfunded. Right? If you look at the budget for the National Science Foundation, it's something like $30 billion, which is probably less than we spend on anything. I think the R&D budget in the U.S. is about $140 billion, where our GDP is 17 trillion, so it's less than 1%. So that makes it difficult if one is not invested in the future to reap out all the benefits, right? For the most part, when you're starting off, it's very difficult to tie that into societal implications. How is my technology bettering mankind, or how is this technology actually going to get commercialized? You're mainly thinking, how do I get this experiment to work? And those are two very, very different things. In my short experience as a nanotech salesman, or I'm pushing instruments now, it's understanding how exactly to solve people's needs. So I do think that scientists do need a little bit of salesman in them, just because, first of all, we're completely underfunded for the most part, and for the second part, to really understand what solutions we can bring to the table that can be transformative, as opposed to just trying to push very novel, high-risk, high-reward ideas, but actually have the public guide us. So I think we're not really good at listening. So I think some of these wounds are self-inflicted, but overall, nanotech is taking off, and I think we've seen some of the things that the organizer, Julian, pointed out are very clear. There's tons of nanotechnologies out there in the market. There's more efforts towards translational research, which means all of the money that people spend in the funding universities is actually getting translated into the marketplace. The importance of commercialization isn't necessarily for some entrepreneur to make money, but to make these technologies available, right? And I think that's what we need. Just get them out there, and once they're out there, the market will weed them out or accept them. But we got to do a better job of getting them out there. And so far we're not bankrupt, so we're pretty happy. So thank you very much for your time.